Hello everyone, and welcome. Have you ever looked at a scientific graph, specifically a spectrum, and seen broad, overlapping humps instead of sharp, clear peaks? It's a common problem in chemistry and physics, making it difficult to identify what you're looking at. Today, we're going to explore a powerful mathematical technique designed to solve this exact issue: derivative spectroscopy. So, what is it? Let's start with a normal spectrum. It's a graph that shows how much light a sample absorbs at different wavelengths. Sometimes, two different substances absorb light at very similar wavelengths. Their signals on the graph merge together, creating one big, unresolved blob. This is where derivative spectroscopy comes to the rescue. Instead of looking at the original absorption data, we apply a bit of calculus. We calculate the derivative, which is essentially the slope or the rate of change of the spectral curve at every point. The first derivative turns the peak of the original signal into a point where the graph crosses the zero line. This zero crossing point very accurately marks the position of the original peak maximum. The second derivative takes this a step further. It's the derivative of the first derivative. It transforms the original broad peak into a sharp, intense, negative peak, which is much narrower. This process has several key advantages. First and most importantly, it dramatically improves our ability to resolve overlapping peaks. That big, lumpy blob can be transformed into two distinct, sharp signals, allowing us to see components that were previously hidden. Second, it helps to eliminate background interference. If there's a constant or slowly sloping background signal, taking the derivative can effectively remove it, making the true signals much clearer. And third, it allows for a more precise determination of a peak's exact wavelength. This technique is incredibly useful and is applied in many fields, from pharmaceutical analysis to check the purity of drugs, to environmental monitoring for detecting trace pollutants. In essence, derivative spectroscopy is a computational tool that sharpens our vision, allowing us to see the fine details within complex spectral data that the naked eye would miss. It's like putting on a pair of glasses that brings a blurry world into sharp focus. Thank you so much for watching and learning about this fascinating technique. If you found this video helpful and want to see more explanations of complex scientific topics, please consider liking, sharing, and subscribing to the channel. Your support is what makes these videos possible. We'll see you in the next one.